Hi, everyone. Today I'm going to walk you through our journey to Imply, what our current scale is, and what are some of the data compaction related challenges that we faced during migration. A little bit about myself first. My name is Neha Yadav. I'm a senior software engineer at Splunk in their observability group. I am a service owner for our Druid clusters, and I was also the technical lead for migrating our AWS-based clusters. I have been at Splunk since 2020. Let's briefly talk about our use case a little bit. Splunk Observability uses Druid for storing high cardinality time series data. Our use case requires streaming ingestion and fast responsive queries. Our data retention is of 8 days. And I would like to emphasize on this, and I will be bringing this up again when we talk about our scale. There are three products within Splunk Observability that use Druid pretty intensively, and each product has its own dedicated cluster in different regions around the globe. Those three products are application performance monitoring, short APM, real-time user monitoring, and RUM in short, and then profiling. This slide depicts the use case. Druid powers some of very powerful interactive features on our application. APM lets the users to troubleshoot their applications, looking at the traces, looking at where the problems might be, and all of the data is coming through Druid. RUM also allows the user to troubleshoot issues via tags and look at their sessions. And profiling also heavily uses Druid for always on, call stack profiling. Let's talk about our scale of Druid at Splunk Observability. Like I said, our Druid clusters are distributed, basically deployed across the globe. We have 21 production clusters. Out of those 21 clusters, there are 17 AWS-based clusters that were migrated to Imply earlier this year. The migration finished in August. There were two GCP clusters that were migrated to Imply last year in November. And we still have two OSS Druid clusters running that we plan to migrate to Imply earlier next year. Let's talk about our scale, on Imply. For our AWS clusters, we all know that Imply offers enterprise hybrid deployment for AWS-based clusters. Since we migrated 17 production clusters, this was, one of our largest migration efforts within Splunk. Our largest AWS cluster contains of little less than 300 nodes. Those nodes include 260 data nodes, 15 query nodes, and 3 master nodes. We have 3 ingest supervisors enabled on our largest cluster with 639 real-time indexing streaming tasks. There are 300 million rows getting ingested per minute, and 3 data sources which contribute to 40 terabytes of unreplicated data. And I would like to bring up our data retention here again, that the 40 terabytes of unreplicated data is a result of 8 days worth of ingestion and not from, like months or years of data retention. Let's talk about our scale on Imply GCP clusters. Our largest GCP deployment consists of 440 nodes. It used to be 330, but was recently scaled to handle Thanksgiving holiday traffic. There are 400 data nodes, 37 query nodes, and 3 master nodes. That cluster has 1 ingest supervisor and has 1,373 real-time indexing tasks running at a particular time. There are 400 million rows ingested for that one data source alone. And that one data source contributes to 278 terabytes worth of data with 8 days of ingestion. So we are really testing the limits here. I wanted to talk about our scale because the next topic that I really want to dive into is data compaction and the challenges that we faced due to the scale of our clusters. Let's talk about compaction a little bit. We all know that multiple Kafka indexing tasks can lead to data being scattered across different segments. Those segments can be uneven, and they can also lead to, they can also impact query performance due to, more number of segment scans. Our use case, like I mentioned, Druid powers really high power, really fast performing, powerful features, and the queries need to be quick responding and interactive. The maximum value of timeout that we have configured on our clusters, on the query side is 30 seconds. So the queries they don't have to be long running, but they need to be responding very quickly. Now, talking about compaction, with the appropriate compaction strategy, we can achieve really uniform segments in our cluster, and that can also help with query performance. Make sure there is no unnecessary memory overhead, and there is lower query time in processing and scanning the segments. Most of our clusters have multidimensional range compaction strategy enabled, which is most appropriate for our use case. But some of our clusters still have dynamic partitioning compaction strategy due to the issues that we have faced. So let's talk about the issues a little bit. So as we proceeded with migration, the very first issue that we saw was just simply lagging compaction. We had, migrated with default configurations. We had like very basic, like compaction spec, which had defined, what our partition specs are going to be, but all other configuration like max rows per segment, split hint spec, segments to merge, all those configs were, at their default values. What we started noticing was that with our very first production cluster that was migrated, compaction started lagging severely. Like within a couple of days, we were seeing that 100% of the segments were pending compaction. And that cluster wasn't even that big. That cluster was barely like 27 million, ingesting 27 million events per minute compared to some of our very large clusters. So in order to resolve the issue, there were some things that we tried. We worked with Imply support and tried out some of the things that did not work for us. Some of them were just, we tried scaling out the data nodes, thinking that we would start getting more worker slots and that would help with compaction. We also tried increasing max num concurrent subtasks. Max num concurrent subtasks were initially set to 6 in our compaction spec. We tried to increase it to 12 and then to even 16, but we were not seeing any improvements. We also tried to increase total num merge tasks, that are like number of tasks that would be, spawned to handle merging of the segments, which was set to 10 by default. And we tried to increase it to 30, but that didn't help either. On further investigation, what really worked was tuning compaction task capacity. And what compaction task capacity is, basically the number of slots that are available for compaction on a particular cluster. So that task capacity is 10% of the total number of task slots that are available by default. So if we had 108 task slots available, about 10% of those would be approximately 11 task slots available for compaction. And we found out that those 11 task slots were not working out. So we found out about automatic compaction API and found out that we could actually tune the slots ratio that would lead in providing more number of slots to compaction tasks. So we tried increasing the task slots ratio to 20%. That gave compaction about 22 task slots. And that is when we actually started compaction, progressing, and we started seeing some improvements. Although even with 22 task slots, we were seeing that somehow only one compact task was running at a time. And we were really surprised by the fact that we had a lot of backlog in terms of the segments that were waiting to be compacted, but we were still seeing only one compaction task being spawned at a time. On further investigating, we found out that even though we had set maximum concurrent subtasks to 16 in our compaction spec, only 4 concurrent subtasks were being spawned at a particular time. So that made us think that maybe we should be switching maximum concurrent subtasks to 4, and maybe that would help in spawning more concurrent compaction tasks. And that is what happened. So with setting maximum concurrent subtasks to 16, we had one running compaction task, since 22 slots by 16 results in one task. Reducing maximum concurrent subtasks to 4 resulted in 5 running compaction tasks, because now we were saying that, for every compact task, we have 4 subtasks that would be spawned concurrently, and that gives us, using 20 out of our 22 task slots that we got after increasing the slots capacity to 20%. So I think it was a combination of both, making sure that our slots ratio is appropriate. If compaction is lagging, making sure that we have enough slots capacity, scaling the cluster, tuning slots ratio, and also keeping an eye on the number of subtasks that might be running at the same time. Like supposingly, if we had all 16 subtasks running, we wouldn't have tuned maximum concurrent subtasks at all. But here we needed to, because we saw that from 16, only 4 were being spawned, and rest of the slots were just, sitting idle, not being used by any of the tasks. The next challenge that we ran into was mostly because we feel that it was mostly because of the scale of the data that we are ingesting, and how range compaction works around that amount of data. So let's talk about multiple dimension range partitioning a little bit. So multiple dimension range partitioning basically compacts the data based on the dimensions that are present in the partition spec of the compaction spec for a data source. What it does is it actually allows for query time segment pruning, because now your segments are created based off of the dimensions and not just based on number of rows. A multi-dimension range compaction task basically runs into 3 phases. The first phase is partial dimension distribution, where these subtasks collect statistics to find what would be the best partition to persist the data into. The next stage is partial segment generate, where those partial segments are generated, and then the final stage is partial segment merge. So it is in this partial segment merge phase when those generated partial segments are actually combined based on the time and value of the dimensions in the partition spec. One thing that we found out was that success of this phase is dependent on definitely how we have tuned our compaction spec, but also on the segment sizes, which is directly proportional to the scale of the data. I would also like to call out that this type of compaction is somewhat similar to MapReduce, where we first are generating and trying to map the data to correct partitions, and in the end we are finally reducing and merging the segments. It is important to appropriately select the dimensions that go in the partition spec, because there are limits around, or there can be consequences of having incorrect or incorrectly ordered dimensions in the partition spec. For example, fewer dimensions can result in really huge segments, and sorting through those large segments can lead to like memory overhead and impact query performance. Just for all your information, I wanted to mention that on our largest cluster, we have, or we had when we started with migration, 8 dimensions in our partition spec. And that partition spec had been working on some of our smaller clusters, so we thought that is going to be appropriate for our larger cluster as well. But what we started noticing was that the third merge phase started failing with Java heap space exception. It was totally unexpected, but the first thing that came to our mind was how different the scale of data was compared to some of our smaller clusters. The first thing that comes to mind is tuning JVM heap size, but we didn't want to do that because we were unaware of the impact it would have on peons and how it would be affecting ingestion. And we did not want to hamper ingestion and cause an outage on our production clusters. There were some things that we really tried, but still they did not work. The very first thing that we tried from our previous challenge was increasing task slots to 30%. We thought that maybe there are fewer tasks running that are handling, large amount of data. So maybe we should begin with increasing the slots ratio to 30%. When that didn't work, we completely stopped range compaction, again, because we were worried about, lagging compaction or failing compaction tasks hampering with ingestion. So we stopped compaction completely and we started executing manual compaction tasks. And we tried a bunch of the things. The very first thing that we tried was reducing the interval that our compaction task was running on. Initially, our compaction task was running on 1 hour interval. We tried manual tasks with 10-minute shorter intervals, that thinking that maybe it is going to handle a smaller subset of data that can result in success of compaction tasks, but that didn't work. We tried reducing target rows per segment, just checking if somehow, again, like handling fewer rows in the segment can help with the task success. We also tried reducing max input segment bytes per task and max num segments in split in spec, just to indicate that compaction task should be handling a smaller subset of data, but that did not work either. We then started tuning our partition spec a little bit. We added one additional dimension to our partition spec, but we saw, that did not have any difference, and the manual compaction tasks were still failing. The last thing that we had tried, actually not the last thing, another thing that we had tried was reducing number of dimensions. Like from 8, we tried reducing the number of dimensions to 5 to 3 over shorter intervals with a smaller number of target rows per segment, but none of the combinations worked. There was one combination that did work though, but that made the manual compaction subtasks run successfully. But what we realized was the interval that the task ran over was from weekend when ingestion was very low. That made us think, and actually confirmed our suspicion that it was all related to the scale of data that a task is handling. We worked with Imply throughout, troubleshooting and trying to resolve this issue. And based on their suggestion, we were able to actually successfully run a manual MSQ reindexing task. But the problem there was we did not have a way of automating, MSQ reindexing task. So there was no way we could, run so many MSQ tasks at the scale of our cluster. So what really worked for us? Based on our experience with our OSS clusters and what we had learned about dynamic partitioning, we fell back to enabling dynamic partitioning. So what dynamic partitioning does is the parallel index task, it runs in just one single phase. And all it does is it combines the segments based on max rows, based on the values of max rows per segment. There are some drawbacks compared to range partitioning. And you can say these are drawbacks only if it matches your use case. For example, if you really need range partitioning compaction to work, then you can consider that dynamic partitioning is like a less viable solution. But there might be some cases where dynamic partitioning would completely suffice the use case. So some of the drawbacks compared to range partitioning are limited segment pruning. So like range partitioning provides much better segment pruning based on the partitions in the dimension spec. We do not have any concept of partitioning by dimensions in dynamic partitioning. What dynamic partitioning does is it does create indexes like bitmap indexes and create segments based on the number of rows. So there is still a little bit of pruning, but still not same as range partitioning. And definitely there are higher number of segments scans for the same query. So if a query is having supposedly running on range compaction segments, range compacted segments, it will be scanning fewer segments compared to if it was running on the segments that were compacted by dynamic partitioning. But still, what we thought was that having dynamic partitioning enabled and having our data compacted is going to be still much better than not having any compaction at all. And again, we thought that this is going to be an interim solution, and we continue to investigate, what would be the solution to the problem and how we can enable range compaction on our clusters. So let's talk about what's next and what are the things that we want to do to have all our clusters on range partition compaction. So the very first thing is moving auto compaction to MSQ. So like I said and explained earlier, we were able to successfully run a manual MSQ task, but we did not have a way of automating it. What we found out was that work is already in progress to moving auto compaction completely to MSQ framework. What MSQ framework does is it helps with executing SQL statements as batch tasks, insert and replace task published segments just like any other batch ingestion. And like I said, like we were able to successfully run an MSQ task, but we were not able to automate it then. Here is a link to the PR if you are interested and would like to follow the progress, of this feature. So we really hope that this feature is available soon and we can test it out and hopefully move our clusters to range partitioning. The next approach that we would like to implement is called the hash trick. I think it is very basic, and we have actually tried it out on one of our dev environments and seen improvements in terms of how uniform our segments became, even compared to range partitioning. So like I said, we have tested this strategy in dev. We saw that it was creating more even segments compared to actually not compared to range partitioning, but compared to the dimensions that we already had in our partition spec. So here is the process that we followed. We computed a hash of each data point, like, a simple SHA-256 hash. We added it to the dimensions in our data source, for ingestion. Then we updated the dimensions in the partition spec of compaction spec. And we made sure that we added it as the last dimension. And also this was the time of updating, adding or removing any other dimensions that we wanted. But this was pretty much it. And after making these changes, when we enabled compaction, we realized that our segments were more even. So that makes us feel that maybe this approach is going to work on our production clusters with larger data scale. The last approach that we really want to try out is running auto compaction on a dedicated tier. So if you remember, I mentioned that the task started failing in compaction task started failing on the merge phase with ohm exception. And we were worried about tuning JVM configs and hampering real-time indexing tasks. What we hope to accomplish from running auto compaction on a dedicated tier is being able to tune JVM settings independently without worrying about interfering with what peons are doing, what happens to ingestion tasks, and making sure that compaction is not competing with ingestion at all. We all know that JVM settings are different for compaction and ingestion. Compaction is more memory intensive compared to ingestion. Regarding GC, for example, for real-time indexing, we require concurrent GC, whereas for compaction, we need throughput-oriented GC, like, parallel GC. So what we did was through Imply Manager, we were able to easily create two tiers. In one of our dev environments, we ended up adding a tier 2 of 2 data nodes and updated worker category on the middle manager using the service level properties. The next thing that we need to do is was update overload dynamic config. So we updated overload dynamic config via Druid console. It can even be done via a post request. Details are here. We need to make sure that we set our strategy to equal distribution with category spec. So this will make sure that the tasks are distributed equally among all the workers. And we also need to make sure that our compaction task actually runs on the new category that we had defined in the middle manager service properties. One other call out here is just specifying a compact task running on the new category will not work. We will have to make sure that we specify that our index tasks and kill tasks are running on appropriate categories. Otherwise, those tasks will run wherever the slots are available. So this is something that we have tested out in our dev environment, and we feel that we would be able to tune JVM separately once compaction is running on a separate tier, and maybe then we can get past the JVM heap space ohming error and make range partitioning work. With that, I would like to conclude my talk. Thank you all for listening.